This is Mohammad Yusuf Najad. I am part of iBrain Group, which is located in Nanjing University of Aeronautics and Astronautics in China. Today, I'm gonna present to you a part of our current research related to the fMRI analysis. Here, we have an example of fMRI data, including a time series of brain image snapshots. We want to present a novel feature selection and extraction for fMRI analysis. The proposed method includes three goals. First, selecting a set of effective snapshots rather than using a whole of the time series. The next is extracting robust features from the selected snapshots, and finally improving the performance of the generated model. Let's start with basic concepts. This is the problem statement. We have different patterns of human brain across stimuli. We try to generate a cognitive model to predict category of new stimulus. Now the question is, which form of patterns are suitable for learning a cognitive model? Well, we firstly rewrite each of fMRI session as a linear model, where D here is the design matrix and we are looking for the beta values. The proposed method here focuses on the definition of the design matrix. As depicted here, the design matrix is technically the convolution of the onset or time points and HRF signal. Here in the left, A, B, C, or D denote time points belong to a unique category of visual stimuli. Based on our experiment, we have two different kinds of design matrix: block design and event design. Now we want to use the design matrix for learning an effective cognitive model. Our approach includes three steps: selecting snapshots, extracting features, and learning a cognitive model. At the beginning, we want to select a time point for each stimulus based on neurological priority. This figure depicts the time points belonging to a unique stimulus. Based on this figure, the brain state in the top of diagram is better to learn a cognitive model. As a result, we are looking for local maximums in each column of the design matrix. Based on this assumption, we define the snapshots as follows, where S is onset, D is the design matrix, G is the Gaussian kernel for removing soft noise, and psi is the whole of the snapshots. These figures illustrate two examples of selected time points, where the blue line is the original column of the design matrix, red is the smoothed version of the design matrix, and green circle are the time points included selected snapshots. As the next step, we want to extract features of snapshots based on an anatomical atlas. As depicted here, feature selection itself has also three steps. As the first step, we map the snapshots to a standard space in order to align them to an anatomical atlas. For reducing the time complexity, this paper uses beta value for each category of stimuli to find a transformation matrix for mapping snapshots from the original space to the standard space. Here, Ti is the transformation matrix. Then we segment the snapshots based on the anatomical atlas, which is here denoted by A. Further, we consider the regions with at least one non-zero voxel as active regions. Based on this, we can rapidly reduce the sparsity of our learning problem. As the last step of feature extraction, we employ again the Gaussian smoothing, this time in the region level for removing noise. Here, L1 and L2 respectively denote the first and the last active regions. There are two examples here for the voxels in anatomical regions. The blue line are the original value of the voxels, and the red lines are the voxels after Gaussian smoothing. Finally, we train a set of classification model based on the voxels in each of anatomical regions and then use ensemble technique for combining them. Well, empirical studies. As depicted here, we employed three datasets provided by OpenFMRI website. This is the correlation analysis in the first dataset for both voxel level in the left and the feature level in the right. As we can see here, correlation of feature level is more discriminative in comparison with the voxel level. This is the correlation analysis for other two datasets. Well, the performance of the classification learning is illustrated in these tables, including accuracy in the top and AUC in the bottom. As we can see here, we provide combination of these datasets in the last three rows where faces, objects, and scrambles are compared with other stimuli. This is the effect of sigma parameter for the smoothing procedure of the design matrix. We have the smoothing equation in the bottom, the best result achieved with sigma equal 1. Further, for sigma between 0 and 1, the design matrix is sensitive to noise, and also for sigma greater than 1, we may remove some weak local maximums, especially in the event-based datasets. And this is the performance of registration objective function by using NMI in comparison with other metrics. And finally, this is the extracted signature from different regions of the human brain for each of visual stimuli category. Let's look at the future works. We propose a feature selection and extraction for task-based fMRI analysis, especially for visual stimuli fMRI dataset. In future, we plan to apply the proposed method to different brain tasks like emotion, risk, and etc. At the end, I have to say thank you for your pay attention.